I'd like to welcome Eric. He's going to be talking about the expanding OME ecosystem imaging data management system, and he's working at the Jackson Laboratory. So let's give a hand to Eric.
Thank you, John. And yeah, thank you all. It's my first SciPy. I'm very excited. It's been very nice 3 and a bit days so far, meeting a lot of people. First, I want to thank the organizers for accepting my talk and for giving me financial support to be here. So I'm very grateful for that. Since it's my first SciPy, and since I'm aware not a lot of people might be familiar with the OME ecosystem, I will start, and actually because I was asked the same question a bunch of times over the last 3.5 days, I will start with a personal introduction and then an introduction of what the Jackson Laboratory is, because that's the question that keeps coming up every single time. And then a little bit about the OME ecosystem itself, and then I'll go into what we have been doing with Python around the edges, essentially. So yeah, that's me. I manage a team of 3 technical experts in the research IT department at the Jackson Laboratory. So think the people that provide HPC, not the people who provide email, even though we are technically in IT. The team is fully focused on imaging data, so it's mostly microscopy. We provide support for data analysis and data management for about 60 PIs. I'll go a little bit more in detail. I have a PhD in physics. Finished my PhD, didn't want to go to the academia rat race, so I started working at a core facility doing imaging data analysis, and eventually moved to JAX about 5 years ago. So I just called it JAX, which is the Jackson Laboratory. We have been using that name before Google and before Mortal Kombat, for that matter. So if I say JAX at any point, it just means the Jackson Laboratory, not the Google one. Yeah, so what is the Jackson Laboratory? It's a biomedical research nonprofit. Yeah, so if you're a machine learning person, it might be confusing at times, but bear with me. So my team is in the research side of things. So there are about 60 PIs in 2 campuses. And that environment looks a lot like a university department. It's PIs with PhD students and postdocs. It's very much like a university. But then there is the other side of JAX, which is how you might have learned and that it exists and might have heard of it, is that we sell a lot of lab mice for labs around the world. It's a nonprofit, so the money goes back into the research, which is great. We do a lot of research on rare diseases, but also in things like cancer, Alzheimer's, like endometriosis, much more. So it's a very varied research environment. As I said, we have 2 campuses with research, and these are the 2 first ones there. So it's Bar Harbor in Maine and Farmington in Connecticut, which is where I work. We have other facilities, so there's Sacramento. We have facilities abroad, like in China and Japan. These other facilities are mostly mouse production, so it's essentially I do not interact with them at all. So that's me. That's JAX. Let me tell you a little bit about the OME ecosystem. So I'm just going to give you a quick primer on OME and Omero, which are 2 connected but separate things. OME is the open microscopy environment. It's a consortium of academic institutions, universities, companies, and it's a consortium that came together to define a common data model for microscopy data. And the OME data model is essentially the thing that's at the very center of everything around the OME ecosystem. And the idea there is you would go from a microscope or any kind of image acquiring device, you would map your stuff from there to the OME data model, and then everything that is OME data model compliant knows what to do with that, knows how to deal with metadata, knows how to deal with everything. So that's essentially the big idea behind this is you map it once, and then all the tools know what to do with that. So if you're dealing with processing data, doing quantitative analysis, visualization, data management, it would all use the same data model, and everything would just work. And to some degree, it does. The hard part is the translation, the mapping. And for that, there's this library called bioformats. If you do anything in microscopy, you know about bioformats. Bioformats is this kind of like small miracle of open source where they reverse engineered like 100 proprietary file formats, and they just have a single library that can read everything. And it's incredible, and it also means that there's no incentive for the companies who produce those proprietary file formats to stop doing that. So it's a bit of a, two-edged sword. It does make a lot of the open source bioimage analysis world work to begin with, because otherwise you wouldn't be able to read data from your Leica microscope unless you have Leica software, or your Zeiss microscope unless you have Zeiss software. So bioformats is the thing that's at the very center of all of this, and it's what makes everything else possible. So I'm going to jump into Omero and what is Omero. So Omero is a client-server application that is centered around the OME data model. So you would ingest data into your Omero server. Your server would do the translation using bioformats. It would store all your metadata in a database that's easily, you can query, you have an API, you can access stuff programmatically. So essentially you import stuff into your Omero server. It's stored in the server. You can do visualization remotely. You can do analysis remotely. You can do whatever you want. And it works. It's great. We use it all the time. So server side, it uses a Postgres database. It uses something called ICE, which is an RPC framework for communication between client and server. It exposes a very nice Python API. And then there's a web front end that uses that Python API to display things. The web front end is based on Django. The front end itself exposes a JSON-based API to the world. And all of this is very extensible. So all of it is open source. All of it is very nice to use. And the front end, so the web part of it, kind of looks like this. It's functional. It's not pretty, but it does work. You have these 3 panels. So on the left, you have kind of like a tree structure of your data. In the middle, you get thumbnails. In the right, you get a lot of metadata. And there you have like 2 kinds of metadata. You have the metadata that bioformats could extract from the original file, and you have metadata that a user added to the image, right? So it could be, I don't know, what species is a sample, or stuff like that. So this is the base web interface that you get out of the box with Omero Web. There's a lot of stuff you can add to it, and lots of ways to extend it. So one of the ways to extend it is, I don't know why this video looks weird. It also looks weird on my screen here, but one of the extensions to this basic web front end is called iViewer. It's a visualizer and, well, essentially it does visualization and annotation of images. So you can pan and zoom in kind of like a Google Maps way, these very, very large images. I don't know exactly how big this image is, but if I had to guess, it's going to be like 100,000 by 50,000 pixels or something like that. And it just works on your browser. It's super performant. It's very good. You can add, you can view, you can edit annotations. So in this case here, you probably saw like people doing contours of cells, and there's this big box that tells you this is a chunk of tissue and stuff like that. Importantly, these annotations are stored in the database, not in the original data. So the original data, as ingested, is always immutable, read-only, you never touch it. You store everything else on top of it. And this is important for many reasons that I'll get to later when I'm talking about the stuff I actually developed. Other ways you can extend that web front end, you have something called Omero Figure, for example, which gives you a kind of like Illustrator or Inkscape-like interface for generating publication-grade figures in your browser. You don't need to download data. You don't need to do any of that. You do everything in your browser. Because Omero has access to your original data, it means that if you need to change like brightness and contrast of a view of your image or anything like that, or if you want to have multiple views of the same image, that's trivial compared to having to either download data or like export a JPEG from your original data, put it into Illustrator, tinker with stuff. So it's probably one of the most popular things we have on the web front end side of things in the ecosystem. So before I tell you 2 stories about the stuff we have done, I just want to touch a little bit on how we work with Python. And there's nothing earth-shattering here. It's pretty straightforward stuff. We test with PyTest. We use Docker and Docker Compose to generate local ephemeral Omero servers to do testing against. We use GitHub Actions for CI, so it's all pretty straightforward stuff, but it works very well for what we're doing. OK, so I have 2 stories to tell, as I said. The first one is something called ezomero. I said that Omero exposes a very nice Python API, and it is actually very nice. It's very powerful. It is super verbose. It's really hard to learn. So over the years, we just started writing a bunch of convenience functions for common stuff that we're doing all the time. And eventually, one day, we just had enough of them that we just went, you know what? We should just bundle this and make a library. And we did it. So essentially, it's a convenience layer library that kind of like abstracts and hides a lot of nuance that you would have in the actual API. The interface is much simpler, much cleaner than the OME provided Python API. The example I have here is code to generate a new data set inside an existing project in Omero, which is a pretty common thing you might want to do. Top part, you're not going to be able to see the specifics of the code, of course, but top part is the Python API as it exists, and bottom one is ezomero. Instead of, I don't know, 15 lines, it's like 3 lines. And it's mostly just taking nuance away, right? Instead of having all these like edge cases that the Python API needs to account for, we just kind of like, most people want to do this, so we have a function that does this. There are a few design principles that we had in mind when we were developing this. One is make it more Python friendly. The original Python API, if you ask the Omero server for an image, it returns an Omero image type, right? And we wanted to have something where if you do a get image, it should return a NumPy array, because that's probably what you want. So we made all our input-output types either built-in or scientific Python, so NumPy arrays, pandas, data frames, stuff like that. We do not want to duplicate anything that already exists in the API. So if there is a function that does what you want to do in the original API, we are not going to have an ezomero function that does the same thing. We wanted to have a kind of like REST-like interface where you're doing posts to create new things in the server, you're doing gets to get things from the server, you're doing puts to change things in the server. We try to keep it as simple as possible, so we try to have a minimal set of dependencies. We try to avoid nuance. We try to avoid complexity. It's very much, if you know what you're doing and you need some of that nuance and that complexity, there is a whole Python API for you, and it's not this. Yeah, so this started as 2 people inside the same institution write these functions. It was me and the person who is now my boss. So we had to make a conscious effort to make it as a community effort instead of just 2 people doing it. So we put the time and the effort to make issue templates, to have a code of conduct, to have a citation file, to have a contributor's guide, and so on and so forth. And it seems to be working. We have plenty of people from outside the institution that are contributing PRs, that are contributing issues. And I was at the OME conference a month and a half ago, and pretty much everyone there knew about ezomero and is using ezomero to some degree. So I think it's a success story. OK, that's story number 1. Story number 2 is something called omero-cli-transfer, which is a bit of a mouthful. But the TLDR on this is, I said that, for example, all the annotations you put on top of your images is stored on the Omero database. So what if you want to move that image from one Omero server to another Omero server? Moving the file itself, the original image, is pretty straightforward. You just move the file and re-ingest it on the destination side. The annotations don't go with it because they're stored in the database, right? So the TLDR is we just made a utility that generates a zip/star file that has your original images plus all the metadata necessary to recreate the exact thing you had in the source server in the destination server. I'm going to talk a little bit more about that. So the problem is, again, that the original images are read-only. They are immutable. You're not writing stuff into the images themselves. Anything additive goes into the Postgres database. So for example, the things that you see in this image here, a user went in there and added what's the species, what's the genotype, and so on. And these things only exist inside the Omero database. If you want that in a different server, you move the data goes, but the metadata doesn't. So if you know anything about anything, you know that what we need to do is serialize that relevant data on one side, deserialize on the other side. This very nice gentleman called Tally Lambert, that some of you might be familiar with, wrote a library called OME types. OME types is a pure Python implementation of the OME data model, which is fantastic. It's exactly what we need to do something like that. So I can use OME types. I can generate a set of Python objects that represent everything associated to that image on the source side. We can export that as, for example, an XML file. We can pack it together with your original images, and then the opposite happens on the destination side, right? So you unpack everything, you take your XML, you deserialize it, and you ingest the images on the destination side. And it works, and people use it, and it's great. But it doesn't do only that, because after you have all that serialization, deserialization machinery in place, there's a lot more you can start doing with it. One of the use cases we have, and it's something we use in-house, is what we call rich imports. The idea of rich import is we use a separate subcommand for omero-cli-transfer called prepare. Prepare creates kind of like a stub XML that points to the images you have in a folder. And then you can edit that XML, add whatever annotations you want to that XML. And we normally would do that using OME types. We generate a richer SML, and then we can use the destination side machinery to deserialize that rich XML and import data with annotations already added to them. And yeah, as I said, it's something we have been using in-house, and it works fantastically. The other use cases we have are using just the serialization part of it. And this is one that I did not predict coming at all. People are using omero-cli-transfer just as an archival or export format, essentially. So it started when people asked me to add an option to export to bioimage archive format, which is a very popular public repo for microscopy data. So I have all the original data. I have all the original Omero metadata. There is no reason why I cannot make a new kind of slightly different zip file that conforms to the specifications of the bioimage archive, so I just did it. And then other people just went, yeah, okay, that's good, but I want something else. So this guy, Christoph Moll, just ran away with it. He made a whole plugin interface for omero-cli-transfer. So there's a whole plugin entry point now, where if you want an extra format exported from Omero, you can just write a plugin and add to it. And in their case, they are using this thing called annotated research contexts repositories, and they just wrote a plugin to export things from Omero to this different format. And yeah, as I said, this is something I did not see coming at all, and it seems to be working pretty well for people. In this OME community meeting, a guy from France was telling me that the whole France bioimaging national effort is now using this for their archival as well. And so all of a sudden there's 6,000 French people that might get angry at me if I do something wrong. Yeah, so those are the two stories I wanted to tell you. So just a quick summary. We use a lot of Omero for data management at scale. So we are talking the tens to hundreds of terabytes of data. We use the existing interfaces for Omero, both in Python and in the command line, and we also extend those interfaces using Python. We developed these two open source libraries that simplify those interfaces and also extend the functionality doing things that were not possible before. Before I finish, there's a lot of people to acknowledge. There is my team at JAX. Peter's here somewhere. He's not here now because he said he already knew everything I was going to say, so he just went watch something else. The folks in Research IT who help out a lot, all the open source projects that we use and contribute to some degree. Josh, Will, and Seb at the OME for all their patience with my questions. And before I end, I decided to put a slide saying reasons why you should come talk to me. If you are interested in any of that, just, find me somewhere. And if you're not interested in any of that, feel free to find me and come talk to me as well. That's it. Thank you.
Thanks, Eric. Do we have any questions? Maybe I'll ask one. Are there any new things that you see developing in OME that you're excited about?
I think the most exciting thing right now is there is a very concerted effort to add the OME data model on top of ZAR. So the OME NGFF specification is what they call it. It's a 0.4 already. 0.5 is coming out. And the idea is essentially to have all this rich ecosystem of tools being able to look at ZARs that come from a bioimaging context and do things with it. So we have this lofty goal of having about 1 petabyte of data using this new kind of like fast-forward format by October this year. And that's the goal for the community as a whole. And pretty much every big public data repository in that space is committed to joining that effort. So it's exciting.
Exciting.
Okay, thanks. How does security work? Is it per user, for example?
Yeah, so Omero has a concept of users and groups. We at JAX just use LDAP or Active Directory for the user authentication, but Omero has its own concept of groups, and then permissions can be pretty granular per group inside Omero. So they don't need to map necessarily to Active Directory groups or anything like that. You can have your own Omero groups. And at JAX, we have a lot of, for example, cross research group Omero groups for collaboration between groups, and it's pretty easy to set up on the admin side of things as well.
Other questions? So you mentioned petabytes of data. Are there any other changes you're going to have to make around OME to support that?
On the data model itself, not really. The tools are probably going to have to change the moment you go above the can this fit in memory limit, essentially. But there we are going to be using a lot of the tools that already exist for ZAR in general, right? So we have Dask already. We have all that ecosystem of lazy loading things, and we can just leverage those things that already exist.
Great. Any other questions? If not, let's thank Eric one more time.